So another class of important derivative shortcut formulas are for inverse trig functions. Now you're probably most familiar with these from buttons on your calculator, sine -1, cos -1, etc. The -1 is not an exponent, it just stands for inverse. Another way to think of these things is as a question that says, what angle do I need to take the sine of, or the cos of, or the tangent of to get this result? So inverse trig functions always produce an angle. Here we need to be a lot more careful about whether or not the functions are invertible. So as an example, we can take tangent. And so if I were interested in the derivative of inverse tangent, I'd have to go back and think about tan and see if it's invertible. And so we could do our usual tan y equals x, our switcheroo, but we have to be careful. The tangent function is periodic. Its period is pi, and so it goes through 0 and it repeats every pi. These vertical asymptotes happen at -pi/2, +pi/2, 3π/2, etc. The tangent function fails the horizontal line test. So in order for it to be invertible, we need to cut out several of the periods. In fact, we need to cut them all out, save for one period. So we are only going to keep the one that goes through the origin, and we will cut out all the other periods of tangent. We will be able to invert tangent only if we restrict y to be between -pi/2 and +pi/2. And in this particular case, we proceed like we did before, and we take the derivative of both sides. As always, this will give us 1. We'll use the chain rule, and so the derivative of the tangent of something is the secant squared of that something times the derivative of the something. And so this gets us secant squared of y times y prime is 1. We'll have 1 over the secant squared of y. We need to be able to rewrite this in some other way. We need to do a little bit of algebra work. The tangent of y is x according to our switcheroo definition, which we could interpret as x over 1. So if we want to come up with another way of writing secant, we can use right triangle definition of tangent. And if we say that this is our angle y, tangent is opposite over adjacent. So we'll have x over 1. And according to the Pythagorean theorem, this will give us 1 plus x squared. Cos is adjacent over hypotenuse. So secant is the reciprocal of that. It would be 1 plus x squared all rooted, and that means secant squared would simply be the square of this, and we would get 1 plus x squared. We end up with this nice little formula. The derivative of inverse tangent of x will end up being 1 over secant squared of y, or 1 over 1 plus x squared. So if we wanted to figure out the derivative of sine inverse of x, we would let y equal inverse sine of x, which means that we would want to switcheroo this. So we would have the sine of y would be x. But of course, we need to ensure that it's possible to do that. The sine is a periodic function, and so it clearly fails the horizontal line test. So in order for it to pass the horizontal line test, we need to take our scissors out and cut it at -pi/2 and +pi/2, and cut everything else out and keep only this section. So it will be 1 to 1 if y is between -pi/2 and +pi/2. The restricted sine function would look like this. We could even put it with square brackets here. It won't really make a difference. And in this case, we do have a function that does pass the horizontal line test, and this switcheroo does in fact make sense. As before, we take the derivative of both sides. We'll get a 1 over on this side, and we'll use the chain rule to say the derivative of the sine of something is the cosine of that something times the derivative of that something. So we'll get cos y times y prime is 1. Or y prime is 1 over the cosine of y. We need to figure out how to get this in terms of the original letter. So we have been told that the sine of y is equal to x, which we could interpret as x over 1. If we were to draw a right triangle and use this as the angle y, sine is opposite over hypotenuse. By the Pythagorean theorem, 1 minus x squared. Cosine is adjacent over hypotenuse, which would just be square root of 1 minus x squared. These angles refer to quadrants 1 and 4. Cosine is always positive in these quadrants. Y prime will then be 1 over the square root of 1 minus x squared. So we get another formula. The derivative of the inverse sine is 1 over the square root of 1 minus x squared. And so there are several trig functions, 6 of them, that have to be inverted and differentiated. So if you proceed the same way, you can get all of them. Now, just like we did with the trig functions, we'll make a little list. There's a bit of a pattern that connects them all. We'll take the functions that don't have the prefix co and list them all on the same side. So sine inverse, tan inverse, secant inverse. These ones, unfortunately, you have to memorize. Once you've got those, the corresponding co-functions have exactly the same algebraic form, except there's a negative in front of each of them. Now, the reality is, because there's a negative in front of them, it's very rare that you want to use these versions. It's usually always the case that you will use the non-co-prefixed versions of all of these things. Once we've got these derivatives, we just use them in our calculations like we normally would. So for example, if we were asked the derivative of the inverse tangent of the cosine of theta, we would use the chain rule. This is the inner part, let's call it u, and the outer part would be the inverse tangent of u. Now note this tan with the -1 is notation for inverse. Sometimes people will use the notation arctan. They both mean the same thing. The -1 is not a power. If we wanted to take the derivative of the inverse tan of something, it would be 1 over 1 plus something squared. That would be the derivative of the inverse tan times the derivative of that something. Well, the something in our case is cosine. So we would get 1 over 1 plus cos squared theta times negative sine theta. So at the end of the day, we could just simply write it like this. So what we have done is essentially come up with shortcut formulas for all of the inverse functions we'll need. And in fact, this leads to all of the functions that we'll ever need to deal with in this course. We've now completed the list of shortcuts. And from here on in the course, we just start using them along with the differentiation rules we know.